thanks for coming. So today we present Attila Jung. Should I pronounce? Is it correct pronunciation?
Yeah.
Okay. From Hungary, and he will talk about fractional Helly theorem.
Yes.
Please.
Thank you. Thank you very much. So, thank you for having me. Thank you for coming to the seminar. I will talk about the Quantitative Fractional Helly Theorem, and okay, I will first explain each word in the title except theorem. I guess I don't need that. Okay, so through the talk, F will always be a finite family of convex sets. Now it will be okay. So this is the main protagonist. And okay, let me start with Helly's theorem. By the way, can you hear me? Let's pick up. Okay. So you can also see the. I think it is this size. Okay. So Helly's theorem. By the way, can I ask you how many of you know Helly's theorem? Okay. Almost. Okay. So we have this finite family of convex sets. And the assumption is that for every subfamily of size d+1, this is how I will denote the subfamilies of size d+1. Okay, so for every such subfamily we have that the intersection of the subfamily, so I will use this notation for an intersection of a family, is not empty. So this is the assumption. And then the conclusion is, then the intersection of the whole family is not empty. Okay. So in other words, if the intersection is empty, then there are at most d+1 of the convex sets showing that this intersection will be empty. Okay. So this was the Helly theorem. Here this number d+1 is optimal. So you cannot just check the subfamilies of size d, for example. It is shown by a simplex of dimension d. So the faces of the simplex are the convex sets, and then we have that every d of them intersect, but all the d+1 of them do not intersect. Okay, so this is, so I cannot write anything smaller here. This is all the Helly number here.
You want F to be at least d+1, right?
Sorry?
If F is too small, then this is not true.
Okay. Yeah. Okay, I will. Okay, F will always be a large enough family of convex sets. Thank you. Okay, so maybe I will make the same mistake for some other statements, but F is always at least, I don't know, maybe 2D or something will be enough. But
Zicha will correct you every time.
yeah, or you can just tell me every time if I need some additional assumption. Okay, so the fractional Helly theorem, we just denote it by FH, fractional Helly, by Katchalski and Liu. Well, here we don't have the assumption that every d+1 of the sets intersect, only that most of them do. So a linear fraction of them intersects, so we have that at least alpha times the number of all the d+1 tuples in F of G is such that the intersection is non-empty. Okay, so this is why it is called fractional, because only a fraction of the d+1 tuples intersect. So this alpha is some real number between 0 and 1. Then the conclusion is that there exists a subfamily of also a linear size. So f prime is of size beta times f, such that the convex sets in F prime intersect. Okay, so we have some weaker assumption and a weaker conclusion as well. So Helly's theorem just says that if alpha is 1, then we can choose beta to be 1 as well. Okay, but the fractional Helly theorem tells us that, that for any positive alpha we have a positive beta, such that if an alpha fraction of the d plus 1 tuples intersect, then a beta fraction of all the sets intersect. Okay. This number d plus 1 is sharp here as well, but here I cannot have just one example like the simplex, because I can just choose beta to be 1 over the size of f or something like that. So we really need a family of examples, but if we just have n hyperplanes in general position, then they will have the property in general position, I mean. Anyway, then they will have the property that any d of them intersects, so a large fraction of the d tuples intersect, actually all of them, but there are no larger intersection. Okay. So this was the fractional Helly, and then we can have, okay, so then the only thing left is the quantitative Helly. So what is quantitative? So the first quantitative Helly theorem, it was a result of Barany, Katchalski and Pach. Here we have the assumption. So here we are not only interested in whether convex sets intersect or not, but we are only interested in the volume of the intersection. So that's why it's called quantitative. Okay, so the assumption is that for every subfamily of size 2D, this time, we have that the volume of the intersection is at least 1. So every subfamily of size 2D have large intersection in terms of volume, and then the conclusion is that the volume of the intersection of the whole family is, well, I cannot say it's 1, but it's something which depends only on the dimension, and it is positive. Okay. So this is the quantitative Helly theorem. Here we have two parameters, this 2D and this V of D. This 2D is sharp. We can just have a really small cube. This will be the intersection of the whole family. We can have it as an intersection of 2D half spaces. Okay, so this is a half space, this is a half space, this is a half space. Sorry, no. This is a half space and this is a half space, and then the intersection of any 2D minus 1 will look like this. So it will have infinite volume, but the intersection of the whole family is something small. So if you don't like infinite volumes, then you can just intersect everything with a large enough ball or something like that, and then every 2D minus 1 of the convex sets intersect in large volume, but the whole family intersect in small volume. And yes, here F should be of size at least 2D, I guess. Is it correct? Okay. So
what is the function VD?
VD, what is the function VD? Yeah, this is the next question. So Barany, Katchalski and Pach, they proved something like d to the minus constant times d squared. And they conjecture that one can delete these two in the function, so it should be d to the minus constant times d. And then Martin also they proved in 2016 that it is indeed one can choose Vd to be d to the minus constant times d, and this constant is between 1/2 and 2, the construction showing that it should be at least 1/2 is just the ball as an intersection of finitely many half spaces, which is impossible, but you can have almost the ball as an intersection of finitely many half spaces. So in this sense it is similar to this one, but you don't have a small cube as an intersection, but a small ball. And then one can compute that it gives this lower bound. And then later this upper bound was improved by Brazicikos. So C is at most 3/2, and this is where we are now. So we don't know the exact constant, but we know the order of magnitude here. Okay, so what is left is to combine the fractional Helly and the quantitative Helly. So this is what we'll do now. So at this point it's not clear, but I mean it should be roughly clear what will be the statement, but we don't know the exact parameters. So I will just name them. So this is quantitative fractional Helly. This is what the talk is about. And then we have the assumption that at least an alpha fraction of the k tuples, so we don't know the value of k now, an alpha fraction of the k tuples are such that the volume of the intersection is at least 1. And then the conclusion is that there exists a subfamily of linear size such that the volume of the intersection of convex sets in this subfamily, it is something v of t 0. Okay, so this is, and then okay, the goal is to like optimize the constants here, or to find the best possible version. So the first such theorem was a result of.
But is it even obvious that this is true just from what you already have, or?
No, it's
No,
yeah. So the first question should be:
Is there a k?
is there a k such that this is and the v such that this is possible? Yeah. Okay, so it is possible. This is a spoiler. So the first such theorem was a result of Sarkar and Sobenon from 2021. They proved that one can choose k to be d times d plus 3/2 and v to be d to the minus d. So this is the first quantitative fractional Helly, and then well, this is much bigger than k in the previous results.
If you put alpha equal to 1 here, then
Sorry?
when you put alpha 1, you get beta 1, or?
Here I think so, yes. Yes, so here even, I mean, what they do is they measure the volume of convex bodies with the maximum volume inscribed ellipsoids, and then you can define their simplicial complex where vertices are the convex bodies, and there is a simplex if they intersect in volume at least. I mean, if the intersection contains an ellipsoid of volume at least 1, and this complex is k Loránd. So
Okay.
so this is really, so it really follows from some previous work on non-quantitative, abstract Helly type theorems. And then, okay, so these two numbers, so this number is just the dimension of the parameter space of ellipsoids. And this number is just how well you can approximate the volume of the convex body by maximum inscribed ellipsoid. So this is the worst case scenario. So when you have a simplex and the ball inside.
I also have a question. So if alpha equals to 1, then beta equals 1, then means if whole family, some large whole family has volume intersection at least 1, then this V function is better than current best bound d to the minus 3 over 2 d
Yes,
here.
yes,
So
yes, yes.
it means that in general case we have a lot of, if this 2d is replaced by some bigger number, then we have
Yeah,
better
so
bound.
here if you are not interested in this 2D, which is optimal, but you want to optimize this V of D, then there are some results. I don't know the exact result, but if this number is exponential in D, then you can have something arbitrarily close to 1 here. So this is like some fine approximation of convex bodies by inscribed polytopes, and then there you need exponentially many vertices, and that's somehow translates to the Helly number. Yeah, yeah, but yeah. So for now we.
That's also by Soberon, by the way.
Yeah, that's also by him and others. Yeah. So here there are like 3 different parameters: this k, this beta, and this v, and we could. I mean, it depends on which one you would like to optimize first, but in general, I think most people start with k, and this is what we will do in this talk. So, okay, so after they prove this result, since these two numbers really depended on the proof method, I guess that's the reason that they conjecture that it should be true that we can write k equals 2d as in the Quantitative Helly Theorem, and some similar volume bound than what is in the Quantitative Helly Theorem. So this was their conjecture, and this is what we started to work on with Mark and Nasodi. So the first result here was ours. This was during my master's. We could prove that one can take Ka to be 3D plus 1. So this is already linear in D, not quadratic as here. But well, the expense was that we had some worse volume bound. Okay, so. And here, where this 3D plus 1, it is really just 2D plus D plus 1, because for one part of the family we use the Quantitative Helly, where this number is 2D, and for some other part of the family we use D plus 1, so we use the Fractional Helly, where this number is D plus 1. So these two numbers add up, and that's why we have this 3D plus 1. So we also felt that this number is just an artifact of the proof method, and we also conjecture that it should be true that we can write 2D here. Okay?
Are the alpha and beta values in the quantitative fractional Helly theorem same as in the
No, they are. I mean, in their result they are the same. I mean, So in this result, it is a later result of Kallai that. We can take beta to be 1 minus alpha to be 1 over d plus 1, I guess. So in particular, this function has the property that as alpha goes to 1, this beta also goes to 1. In their result, I think they have the same. In our result, it's not the same, and it's not even going to 1 as alpha going to 1. Yes. So there are like 3 different parameters. I am most interested in k, then v, and then beta. But so I will not even mention beta here. But yes. So yeah, it can be an open question to optimize beta in all these cases. Okay, so we also conjecture that that it should be enough to write k equals 2d here, and then well, I continued to work on this, and then I was able to improve it after a year. K equals, what's your guess?
3D.
2D? No, it's just 3D. One less, so still we have some work. Okay, left. Okay, so this is, and then, well, v of d, it was d to the minus constant times d cubed, so it's something worse. So we are losing control of the volume bound at this point. Okay, so and this was really based on a work of well, it was based on two works. One is the Quantitative Colorful Helly of Domásdy, Földváry and Nassaudy, and the other is the work of Andreas, who proved that colorful Helly implies fractional Helly in a fairly abstract sense. So what is colorful Helly? CH stands for colorful Helly. So it was first proved by Loránd. Well, he posed it as a practice problem in some Hungarian journal, so it's not a real publication yet. But later, Barany proves something called the colorful Katchalski theorem, and then he published the two theorems together. So what is the colorful Helly? It's about not one finite family of convex sets, but d plus one of them. So we have f1, sorry, f d plus 1 finite families of convex sets in R to the d. So they are like the color classes, so we can have blue and red and yellow convex sets on a plane, for example. And then the assumption is that every colorful tuple intersects. So whenever we choose one convex set from one family, whenever from the second, last one from the last family, then they intersect. And then the conclusion is that there exists an I such that the I's family is intersecting as well. Okay, so yes, and then one can look at these theorems as like hypergraphs, and then this will become a forbidden hypergraph in a d plus 1 uniform hypergraph, and then one can formulate the fractional Helly also as property of hypergraph. So this is some very strong Loránd type property of the hypergraph. We have like very large cliques if we have a dense hypergraph, things like that. And then Andreas proved that in this abstract sense, colorful Helly implies fractional Helly. And then there was a result of Domásdy, Földváry and Nassaudy, which is a quantitative colorful Helly. So this is quantitative colorful Helly by Domásdy, Földváry, Nassaudy. And here we have 3D families of convex sets. We have that every colorful tuple, the volume of the intersection for every colorful tuple is at least 1, and then the conclusion is that there exists an I such that the volume of the intersection of the I's family That is some d of d. Okay, and then I just combined the result of Andreas with this. I mean, here we have more than one hypergraph because we have the convex sets intersecting in volume 1 and the convex sets intersecting in some smaller volume. And then, okay, I just adapted the method invented by Andreas to prove this theorem. But this here K also depended really heavily on the proof method because I just reduced the quantitative fractional Helly to the quantitative colorful Helly. So I also conjectured that it should be enough to write K equals 2D here. Okay?
So
Yes?
maybe it's not a very important question, but do you have a strict inequality between the volume and VB? Okay.
Yeah, it's not, yeah.
In this 3D is tight number for quantitative colorful Helly.
It's it is conjectured that it should be 2D, as in the. I mean, this colorful Helly is really a generalization of Helly's theorem because if you, I mean, these families need not be distinct. So if they are all the same, then the assumption is just that every d plus 1 tuple intersect, and the conclusion is that then all the sets intersect. And also here, if they are all the same, then the same example showing that the quantitative Helly, this number cannot be lower, shows that here we need at least 2D families, and it is conjecture that it should be 2D. I think this is one of the most interesting open questions left here, and that's why it is so, because we joined forces with Nora and Istvan, so Nora Frankl, me and Istvan Tomon. At the beginning of last year, we were able to prove the conjecture. So K equals 2D, and V of D something d to the minus constant times d squared d. Sorry, so it is what they conjectured. Actually, this volume bound is really coming from the quantitative Helly. So, and this number is also coming from the quantitative Helly. So, at this point, so this proof really depended only on the quantitative Helly theorem. So we felt like it is like quite natural. It's not just an artifact of the proof. It should be the right number. And then we started to think about the how can we make extremal families. And as I said, yeah.
But the beta here is what beta are you using?
It doesn't go to 1. It's not. It is not terrible, but it doesn't go to 1. So that is an open question whether here we can have beta going to 1. Yeah. So.
So when alpha is 1, then what kind of beta you get?
So when alpha is. No, sorry. Yeah. Yeah. If alpha is 1, then beta can be 1. And I just forgot that in this paper, I also proved that if alpha is very close to 1, then one can take k equals 2d. So in this paper, there was a partial result that k can sometimes be equal to 2d if alpha is very close to 1.
Okay. I meant
it's
limit of when alpha.
Yeah.
Limit when alpha tends to 1. It might not necessarily be 1.
So we have here that, I mean, combining these two results, I mean, the other result in this paper, which I am not talking about, I didn't state it like, but yeah, so it's it is also based on your paper. I mean, the quantitative, the hypergraph chain version of your method. Yeah, so here beta is going to 1 when alpha is going to 1. Yes?
Also, on a slightly different note, in all these results, how tight is the bound on the V function?
On the V function, I mean,
Can it be 1 over
here it is like,
I mean,
we don't know the order of magnitude for V, I mean for quantitative Helly. For the other results,
okay, so
So you can't do better than 1/2 that constant.
no, I don't mean by the constant. For example, can you give a bound of volume to be at least 1 by poly d? This is currently 1 by exponential in d.
yeah, it's 1 by exponential in D, and it should be like that. I mean, when I wrote, let's see, has to be at least 1/2.
Okay.
That means that there is an example where all the 2D tuples have volume 1, but the whole family has volume d to the minus d over 2. Yeah, so it cannot be a polynomial. Okay, for the fractional Helly, we don't know yet, so we are still in the process of, I mean, at this point, yeah, we just focused on the Helly number. And okay, and then when we prove this conjecture, we
But k could be less than 2.
yeah, that's the question.
Oh,
Okay. So at this point we
Spoiler.
yeah, spoiler.
sorry.
Yeah, this is okay. So this is what happened. Okay, now it's just okay. Okay. So we started to have an extremal example for this one. It turned out that there is no extremal example, as Andreas pointed out. But okay, so why doesn't an example like that work? I mean, this is first of all, this is a very finite family or a bounded site. So this is just one example. But the worst thing is that whenever you have just half spaces, it will always be true that either half of the half spaces are looking upwards or half of them are looking downwards, and then the intersection of those will have infinite volume. So without any assumption, any k and alpha and assumption like this, we have that half of the family has large volume. If we just have half spaces, so in the non-fractional cases, it is usually enough to prove the theorem for half spaces, because then you just approximate convex sets by half spaces, and you can just replace the convex sets by the generating half spaces and use the theorem for them. But for the fractional Helly, it is not possible, and it is not possible to have an example with half spaces. Okay, so the only example we found is this example where we have hyperplanes in general positions where they do not have volume. So, but we can make them a bit thicker, and then we can have an example where every d of them intersect in volume 1, but no larger intersection is there in the family. And it turned out that this is the truth. Okay, so with the same co-authors, we proved that k can be d plus 1. Well, Vd is, I just say that it is positive. Okay, this is something very small at this point. You will see from the proof that it really depends on some like hypergraph Ramsey numbers. So it is 1 over 2 to the 2 to the 2 to the 2 to the something, where the tower is of height OD or something like that. So this is really much worse than exponential, much worse than this one. But at least this is positive, and k is just t plus 1. Okay, so this is what this is the result I would like to prove or sketch the proof of today. If you have any questions about the statements so far, then feel free to ask. Okay, if not,
So is,
Yeah,
there,
sorry.
is there any evidence on like that VD coming from hypergraph Ramsey? Is that supposed to be close to truth, or
We have a feeling that it might not be sharp. Yeah. So yeah, it can be. Yeah. Okay. So the best possible. So the best possible case. So it can even happen that this volume bound is arbitrarily close to 1 at the expense of beta. So if this beta can depend on, so here in the quantitative fractional Helly, this beta it only depends on k and alpha. But if this beta can depend also on so if this beta is beta dimension k, alpha, and v, then maybe we can, for every v arbitrarily close to 1, we can have a small enough but positive beta. So maybe for every v there exists such a beta, for every v smaller than 1. So this is the strongest form that we cannot refute. Yeah. So maybe here we can even write 1 minus epsilon at the expense of beta. I mean, I'm not sure whether I believe in that conjecture, but this is the strongest form that might be true. Okay, so so what we did for to prove this result, the first part is nowadays a fairly common method for like lowering fractional Helly numbers. It is based on a paper of Barany and Matuszek on convex lattice sets. So there was this paper of Barany and Matuszek about convex lattice sets. So we have convex sets, but we are interested in whether the volume contains a point with integer coordinates or not. And there they proved that the fractional Helly number of the integers, in this sense, it is d plus 1, and previously it was only known that it is at most 2 to the d or something like that. So the Helly number here, sorry, it is 2 to the d. So this is one case where the fractional Helly number is much smaller than the Helly number. So this is not the first case where it happened. It happens many times. Okay, so what they do is okay. So maybe I will start to define some things for the proof. So the first part is really based on their method, and then we will have a lemma which was the new part. So what we added. Okay, so we will have not just one hypergraph, but a sequence of hypergraphs. So let me check how so HVK, so such that the vertex set will be just our convex sets, and the edge set of the hypergraph is just those k tuples from F which intersect in volume at least V. Okay, so we have these hypergraphs. The assumption of this theorem is that age 1 d plus 1 is dense, so an alpha fraction of all the edges are present. Right? It is alpha dense. Okay, because we have an alpha fraction of here of all the k tuples have volume at least 1. And then what we know about dense hypergraphs, we know that they contain a lot of like if it is a dense d plus 1 uniform hypergraph, then it contains a lot of complete d plus 1 partite hypergraph of fixed size. This is a D plus 1 partite.
Oh, yeah.
Yeah, yeah. I mean,
Mhm.
it is not true for D plus 2 partite, but yeah. So if we so I will denote the complete D plus 1 partite hypergraph where every part has size t by k d plus 1 t. So this is just, we have d plus 1 classes, and then every class has t vertices, and then every colorful tuple here is an edge. Okay, so these are not the edges, these are the partite classes, but everything here, so this is an edge, this is an edge, and things like that. So this is a complete D plus 1 partite hypergraph, and then there is a result of Eötvös and Simonovic. That if we have a dense hypergraph, then positive fraction of all the possible copies of k d plus 1t is present. So if the edge set of the hypergraph is some alpha times all the possible edges, maybe I just write d plus 1 because I will only look for d plus 1, then there exists some gamma times n to the, well, how many vertices this guy has is t times d plus 1. So there are this many distinct copies of k d plus 1 t in H. Okay, so this is some extremal hypergraph result. Okay, and why is this good for us? Well, this hypergraph, it really looks like the one in the colorful Helly, right? So we have these d plus 1 color classes, and every colorful tuple intersect in volume 1. That's what it means in terms of the of convex sets. So then we will have a lemma saying that for every such configuration, so whenever we find k d plus 1t in this hypergraph, then we also have a 2D tuple which intersect in large volume. That will mean that if H1 d plus 1 is dense, then H something 2D is also dense, and then we can just use the previous result. Okay, so this is like a stepping up lemma or something. So we will reduce this theorem to this theorem by this method. So the lemma is that we have f1 f d plus 1, each of size t, which is large enough. We have that for every c1 in f1, c d plus 1 in f d plus 1, the volume of the intersection is at least 1, and then the conclusion is that there exists an fi such that there exists, well, I shouldn't call it C, so maybe K1, or maybe, okay, D, D1 up to D2D in Fi such that they have an intersection of volume at least some W. Okay. So let's compare this to the colorful Helly theorem. So first of all, it has only D plus 1 families, and I said that there is no quantitative colorful Helly with D plus 1 families, so there should be at least 2D families. But this lemma is much weaker than than a quantitative colorful Helly, because first of all we need that every Fi is large enough. This is one thing, and then the other one is in the conclusion we don't have a whole family intersecting, only 2D sets from one of the families intersect. Okay, so this is, and then if we have this lemma and we have this result of Eötvös and Simonovic, then from the fact that H1 D plus 1 is alpha dense, we know that there are a lot of like configurations where we can apply this lemma, and for every application of this lemma we get an intersecting 2D tuple which intersect in some omega. Okay, we want to show that H omega 2D is dense, and okay, so one problem can be that for different configurations we find the same 2D sets, right? So it can happen that these D1 up to D2D are part of this configuration, but if we change some other families here, we just have the same 2D intersecting. So we need to do some double counting. Yeah, it is just some simple counting, yeah.
So where does T appear in the lemma? The size of F?
T?
Yeah.
I mean, yeah, it should be large enough. This is also some hypergraph Ramsey number, so this is large enough.
Maybe it should be at least 2D.
Okay, it's a function of D. T
This-
is a function of D.
T is a function of D, yes.
Okay.
T is a function of D, a very large function of, or very fast-growing function of D. So we need that H omega 2D is dense, but then okay, so we have from Eötvös Simonovic we have a gamma fraction of all the possible subconfigurations like this, and we know that every 2D set can appear in at most n minus 2D choose T times D plus 1 minus 2D configurations like this. So this is still at least some alpha prime times n choose. Oh, sorry, n is the number of sets in F. And choose 2D. So this is just some double counting that on average. Okay, so every 2D tuple can be chosen this many times, but we have this many configurations, and it is still large enough. Okay, so this is what we already knew when we started thinking about proving this fractional Helly for with k equals d plus 1. So this is the new part is how to prove this lemma, and I still have 10 minutes for that. Okay. Okay, then I will try to be very quick. Okay, so what we will do is, so we have these families, and then we assume that the lemma is not true. So every colorful tuple is intersecting in large volume, but any 2D set from one of the families, they intersect in some very small volume. Okay, and then what we will do, I mean, sorry, I will be not too formal at this point. I just want to give you an idea of what we are doing. So we have F1, or actually F subfamily, and then we look at every 2 device intersection here. So they are like very small convex sets somewhere in the space, and we just want to make these intersections empty, right? Because if we can make every such intersection actually empty, then it will contradict the colorful Helly theorem which is here, right? Because then the colorful tuples will intersect in, well, a large volume, but what we are interested in is that it will intersect in at least one point. But if we can make these small intersections empty, then we are done. And then we want to like cut these intersections out from the space, which is not a very good idea if you have convex sets, because if you just delete these intersections, then the convex sets become non-convex, right? I mean, there will be holes in the sets. So what we have is that we can enclose every such small two-device intersection with a simplex, with a still small simplex, such that, I mean, if these intersections are really small, then it will be true that the union of these simplices are still like less than one or so, less than 1/2, something like that. And then whenever we have a large colorful intersection, it will be a convex set like this. And if we cut these small pieces out, then this large intersection will remain large. I mean, volume at least 1/2 or something like that. But it is not convex. So what we do is we partition the space using the face hyperplanes of these simplices into bounded many regions. So this the number of regions, it really depends on the size of f1 prime and the dimension. And then we want to restrict every colorful intersection to one of these regions. So for example, this large intersection we just restrict to this region if, I mean, by pigeonhole principle, one of these regions will be large inside this colorful intersection. And then we want to restrict our sets in the other families such that they only intersect here in something which is convex. Okay, but for different d-tuples here, we might need a different region, and there is where we are using hypergraph Ramsey. So here we view it as a d-partite, d-uniform hypergraph, and for every colorful intersection we introduce a color if you are to use Ramsey. And then we can find a large sub-hypergraph here, where every intersection is of the same color, and then we can just restrict the sets there. So this is, I think, I'm sorry that this was the most interesting part, but maybe I stop and then we still have some time for questions.
Thank you. Any questions?
Yes.
So if you have the 2D in the quantitative colorful Helly, would that give you a better VD?
I mean, if we had 2D in the quantitative colorful Helly, that would improve this result. I mean, this is based on the quantitative colorful Helly. So it will improve this 3D to 2D, but we already have that. But we also need the volume bound, and it will not improve the volume bound, because in this proof we need to use the quantitative colorful Helly actually 3D times or 2D times, and that's why the exponent is even bigger. So yeah, so this is not the best way to improve the bound. Yeah.
What if maybe you don't need those 2D sets to belong to some fixed family at Phi?
Yeah, it doesn't really matter. Yeah, I mean.
So then you could use Helly instead of Phi. I mean, could the proof be simple, or could something be improved, or?
Yeah. So this result is only true for these D+1 partite
Yes.
hypergraphs.
So whenever you see such a D+1 partite, all
Yes.
you need is that there are some 2D whose intersection
Yes.
volume is large. It
Yes.
doesn't have to be inside one Fi.
Yeah, yeah.
Mhm.
It doesn't have to be. I mean, it's just this is just what we could prove. I mean,
Mhm.
if you can, I mean, yeah. So we are losing a lot here because this omega is much smaller than 1. This is where the hypergraph Ramsey comes in somehow. So if you can improve this lemma somehow, this would really improve the volume bound here and also the beta in this result. So
So
Yep.
in your another result, the case, of course, to this, I remember you mentioned you follow similar improvements of the Barany Katchalski.
yeah, so this one actually is just a simpler version of this proof, but it's actually improved it. So yeah, this is. I mean here we used quantitative Helly and fractional Helly both, and that's why it became 3D+1, and then 2 years later we just observed that we don't need fractional Helly really. We just need. I mean, yeah. So this is really, and this proof is almost just a subset of the proof from here. So this is, yeah, my bad.
And you don't have any collapsibility of Loránd, like the solar.
You only have collapsibility or Loránd if you have k equals this number. I mean, below this number it will not be. I mean, even here it is. I mean, it is only k Loránd if you define the simplicial complex such that there is a simplex if the convex set contains an ellipsoid of volume 1 and not if it has volume 1. So it is really important to use these ellipsoids.
So when you define such a simplicial complex, you don't really care about VD, or so just to think about the
Yes.
volume is less, so greater than or equal to 1.
I mean, yeah, but then by volume you mean volume of the maximum inscribed ellipsoid, and that's why you have this volume bound, because if you approximate everything with the ellipsoids, then you at the first step you can lose this volume. But after that you will not use any volume from the ellipsoids. Yeah. But below this number there is no Loránd even with these ellipsoids.
So do you think that you can use any other measures?
Yeah. So our proof, which I didn't really have time to explain, but it doesn't really use the properties of the volume. I mean, you just need that if you have a small convex body, then there is a small simplex around it, and then if you cut a convex body into bounded many pieces, then one of the pieces will be still large. I mean, if the original convex body was large. So this is in particular true for example, diameter, and then for diameter there are also quantitative Helly type results where you just replace every volume here with diameter, and there the best result before us was k equals 2D, and we also improved that to k equals D+1. And maybe you can also look at the other meaningful. So diameter is not even a measure. I mean, it's not, yeah, it's something measure-like, or yeah.
So is there some geometric meaning of that function, like a d to the minus d and d to the minus cd? So
Yeah, I mean this d to the minus d, it has a geometric meaning. It's the best approximation ratio of the volume of the convex body by the volume of the maximum inscribed ellipsoid. Yeah, so this is.
So what was it, ratio?
Yeah, so if you have a convex body of volume 1, and you want to approximate it with the maximum volume inscribed ellipsoid, then that ellipsoid can have volume d to the minus d.
So does your theorem give some equal time result? Or
So this
Yes,
is
it does,
considered
yes.
in this way.
Yeah.
so
So
you don't have any serious problem with applying weak epsilon.
yeah. So there is this paper of Alon, Kalai, Matusak, and Meshulam where they prove that fractional Helly implies PQ
Yes.
in an abstract sense, but they also use this one hypergraph setting where you only have one type of intersection. But it turns out that can also be generalized to this more than one hypergraph setting. I mean, it's not written down anywhere, but this is what we do in the papers when we. I mean, yeah. I mean, if you are not using some induction on the number of sets, then usually the proofs go through. I mean, these abstract proofs also work for these hypergraph chain things.
Right. Any other question? If not, let's thank speaker.